sort of like, let's assume we see, for example, as one scenario, let's assume we see some mild excesses in some channels. The question will be, how do we construct the next generative model from there? Historically, this is sort of handcrafted, more or less. You have a very good idea. You deduce your consequences, you compute your observables, you fit it with the data. If the fit matches, you fly to Stockholm and get your Nobel Prize. I propose that sort of an alternative way where machine learning is sort of brought into the game for constructing the next general model. So the idea, what I've picked up on is Ian Goodfellow's idea of generative adversarial networks. I don't know how much you guys are familiar with what is going on in machine learning. This generative adversarial networks is currently sort of like the buzzword. It's like the big player after long short-term memory algorithm was before. Now everybody talks about guns. So I'm jumping on sort of like something that is super, super trendy in the machine learning community. And the idea, very loosely speaking, is that you have two neural networks. In his case, it's neural networks. I call them machines because for me, I don't care if it's neural networks or something else that optimizes some function. For me, neural network is just one of many options. So the idea is that you have two machines, be they neural networks or something else. One I will call G, that's the theorist, who comes up with new models, maximizing some criterion that I want to discuss what it could be. And the other machine will be, I call him D, or her, the data analyst who tries to disprove that theory. And they play a game. It's really like in adversarial networks, it's really a game theoretical framework that Ian Goodfellow set up. So they're playing a game. Both machines try to optimize, maximize a function, and hopefully they end up in a Nash equilibrium. In that case, sort of in the most visionary case, the optimal sort of the Nash equilibrium would correspond to the next generative model that describes all the observations. Yeah. So, two machines. What could these machines look like? The generator G, the theory, like that's the guy who has to come up with models, with ideas. What could that guy look like? So to discuss what that guy could look like, there is two ingredients. One ingredient is what loss function could that guy maximize or minimize? What objective function? What should it try to do as good as it can? And the other thing is it always needs to walk in some sort of a parameter space. So what could that parameter space, the model space, look like? So these are the two questions that I think need to be addressed. So I have a few proposals. I'm giving you an idea, right? I'm not giving you a finished piece of work or anything close. So for the model spaces, I think an easy way is the models that we have used so far that we know are well established, we understand them. So the usual suspects would be CMSSM, PMSSM, non-universal Higgs, composite Higgs, twin Higgs, little Higgs, I don't know, like all these guys. The pro is that for these guys, we really have like all the tools are in place, so we could take a model. We have the number of degrees of freedom is fixed in such a model, right? The CMSSM has 4 + 1 degrees of freedom. So in that case, it's really like it would, the machine would walk through parameter space and it would optimize these parameters. So it would be like, I would think of it as an optimization. We could, as soon as I define a point, I think all the tools are there, right? We can compute cross sections. We know the theory works, it's complete and everything. But yeah, it's not really sort of, like it's fairly confined. The alternative, and I have to state that I don't know too much about UFO files and how to use them and how well they're covered and what I can do with them. But the alternative file, at least conceptually, I find it very intriguing if we had such a generator machine walk in sort of like UFO space. And in UFO space, as much as the way I understand it, Benjamin, correct me if I'm saying something silly now. The way I understand it is I can write down any coupling, so I could basically at least sort of let the machine invent any kind of Lagrangian. The number of degrees, I mean, I can add whatever I want. The number of degrees is not fixed. I don't know about tools, about like if I have a machine, a generator that works, that is based on UFO files, I don't know how easy it is to state that it's renormalized, like the theory that I'm writing down is like follows all the quantum field theoretical constraints or not. I don't know about that. Yes. Yes, and not the other way around. Well, that. Uh-huh. Yes, I'm actually thinking of the Lagrangian. Yes, I'm stating I've never used UFO files, so I don't know if. Yes. Yeah, anyways, like a Lagrangian. Any Lagrangian, and the generator just walks in the space of all possible Lagrangians, optimizing some sort of a loss function. So I think that's the next question. What kind of loss function could that be, or objective function? Yes? Okay. I'll look it up. Cool. Yeah, yeah, I am. Okay, loss function. So I guess there is two. I will differentiate between two scenarios. One scenario is that we see mild excesses here and there. And statistic dictates that this is going to happen. If like if by mild excesses we mean 2, 3 sigma excesses, this is going to happen, right? So like purely statistically, this is bound to happen. In that case, the generator could optimize the compatibility of the model with the positive results. In the absence, so I'm proposing, you see, I'm proposing like a set, sort of a framework in which you can play a few games. This is the idea that I'm proposing. In the absence of signal excesses, it could optimize something that I will call discoverability, or something I would also loosely call embarrassment. So it will maximize embarrassment in the sense that you have a model that should clearly be disproven, falsified by the experimental data, but we cannot. So the generator could maximize this, this embarrassment criterion, or any other criterion. Yeah, discoverability, for example, if we have a criterion called discoverability, that criterion will clearly be like the most important aspect would be the cross-section. So the generator could try to come up with a model that has a very big cross-section, but nevertheless, it's not falsified in the experiment. And then you could go and say, oh, this is interesting. Why can we not falsify this? And then the next criterion will be, for example, how much energy should be deposited, should be visible to the experiment. That's sort of the second order interesting quantity that could go into such a loss function. So that would be the generator, the theorist AI. Yeah, and then, well, this is a technicality. And yeah, and I've not yet, I don't even bother yet specifying how you would optimize that. You could do it with neural networks, but there's no need. There's probably you do not want to do that with a neural network, but that's sort of like, that's not yet. There's not yet a need to discuss these technical details because it's still too vague, obviously. So on the D side, what could a theory falsifying data analyst look like? The D, sort of the opponent, the other player, the experimentalist player. And sort of the first idea, the first naive idea would be, think of a mathematical space of all possible analyses, searches that you could do. And how about this, the D machine optimizing, choosing that analysis that maximally is expected to falsify the theory. So this would be the mindset, this would be the ideal. But of course, like, if I define my set of all possible analyses that I can even think of, I would have to have at least the expected, if we think in terms of signal regions, I would have to have at least the expected number of background events in all these possible analyses. So clearly that is not possible, or like not technically really feasible. So this seems like not a way to go forward. The next thing that I will come up with, we take the analyses that exist, but we reinterpret them, but also that will be time consuming. So I've been thinking, what if, you know, Andre, Sabine, and I, we have worked a lot on simplified models. Can we exploit the notion of simplified models to realize such a discriminator machine? Because simplified models, the way we introduced it, like 6 years ago, was exactly that, as an abstraction layer between the experimental data and the model building. So a language in which we describe the data so we can actually do the model building step independent from this abstraction step. So what could that look like? And here we do have a tool that sort of works towards that goal. It's like models. So the idea is we built this data analyst on top of models. And in models, we have the database of experimental results. And if we extend it to new signatures, like what we want to do. Sorry, Andre, I thought you would be giving a talk. And we extend the statistical, if we also extend the statistical capabilities of models, we could have a discriminator machine that works on top of this models database and looks up like all the signal regions on all the analyses and looks up that, tries to find that combination of signal regions and analysis that maximally excludes the model at hand. So that would be the game we can play, and that would be realistic. That would even be fast. So we've been working a lot on extending exactly, this is what we're doing now anyways. We're extending, we want to extend models on the statistical side and on the physics side anyways. So here's the statistics side. Ever since recently, the experimentalist, this is like our big topic. Where's Nick? Yeah. So we are being given like these very big, beautiful covariance matrices. And I have a first implementation in models that shows that we can really make use of it. So this is what we're doing in the official models. If we're given that, like 84 signal regions by the experiment, what we have done so far is we've always chosen just the best signal region, the result, like the best expected result. We've chosen that signal region, and we work with that. And now we can combine, thanks to this beautiful covariance matrix. So what we see here is this is actually a CMS result. This is one mass parameter. This is another mass parameter. This is the official exclusion line given by the experiment. The points are connected to models. Green means models cannot exclude these points. Red means models can exclude this point. And we see that with the best signal region, we have always been conservative. And this, I mean, this is expected because we don't exploit the full information that is there. So when we choose the best signal region, we're like, I don't know, 200 GV conservative. If we fix the delta M, this parameter here, we would exclude up to here instead of up to here. If we combine, obviously we can beautifully reproduce. In that case, we can beautifully reproduce the result. So we can combine the results with signal regions. This is actually sort of a technical thing. We do have, in models, we do have results that are based on upper limits, and we do have results that are based on efficiency maps. For efficiency maps, we can easily produce a likelihood, and we can then combine these likelihoods. For upper limits, we can do something very crude. We can also produce a likelihood given upper limits if we are also given the expected upper limit. Because if you have the expected upper limit and the observed upper limit, and we assume that in very crude approximation the likelihood is Gaussian, we can fit a truncated Gaussian distribution with these two values. So we could, in principle, this may be historical or not, I don't know yet, we could in principle also create likelihoods from upper limit results if the experiments just give us experimental upper limits and not efficiency maps. And so we can combine. The discriminator needs its sandbox. This is what I'm trying to convey here. For the sandbox is the set of results that it can combine, and from that it should build sort of like its combination that best excludes the model. So to give step one step out again. So we can combine signal regions, and this indicates work in progress. So I don't want anybody to take like the explicit value seriously. But what you see here is this is the models database, the way it is now. all the experimental results on the x-axis, all the experimental results on the y-axis. If a certain bin is white, it means that at least for either the x or the y, we cannot create a likelihood that we can later combine, because we probably only have the observed upper limit result, and from the observed upper limit result alone, we cannot compute the likelihood. Green means, like the color dots mean that for both elements of the pair, we can produce a likelihood. We can construct a likelihood. If it's green, it means we can construct a likelihood for this result. We can construct a likelihood for that result. And we are in crude approximation safe to what I call trivially combine these results. Trivially meaning like we assume that there is no correlation. Red means we know that there is a problem. We cannot combine these results. So this together. So here, what the discriminator machine, the discriminator bot can do is it can find like all the combinations, all the sets of analyses that show up as green here. It can combine, and it can see if like the combination sort of better excludes the generative model that the generator came up with. So that together, these sort of technologies or these ideas together should hopefully give the discriminator a big enough sandbox to play and to come up with the optimal combination. And this is actually similar. Let me cite here these guys. These guys, what they did is actually something a bit simpler. They had, this was also done outside of the experimental collaborations. So they took, I think, the same analysis with 80 signal regions, and they looked for the combination of signal regions that is most interesting within this one analysis. So we would do something similar, except that because we introduced the notion of simplified models, we can go beyond just one analysis, but we can combine several analyses. You cannot, I think, I do not see a way of doing this without introducing the notion of simplified models. So in that way, we would do the same game, but because we are using simplified models, we could go beyond just one specific analysis. A word of, so far I've only talked about exclusion and negative results. So how will we include positive results in the whole framework? I think there is a natural way to do that. And with positive results, I'm saying like even like 2, 3 sigma excesses we could describe as we could consider like as a tentative signal and see what the machine would give us. Like what's the best way to describe this tentative signal or this dispersed signals or something. And what I will propose is, again, based on simplified models. And I would decompose sort of the procedure into several steps, 2 or 3 steps. The first step would be one would have to identify the set of simplified models that best describe the positive excess. Step number 2, parameter inference. Just we maximize the likelihood. We estimate the parameters. Usually it's mass parameters. And this we will do for every mild excess that exists. So we would have several of these sets of simplified models with estimated parameters. And we would incorporate these positive results, I think, in G. Possibly one could even also do it in the D, in the discriminator. So here I'm not entirely sure what's the best thing. And yeah, and this effort can, of course, this can be done outside of the experimental collaborations, but it can also be done inside of the experimental collaborations. So, Wait, we will compute the base vectors. I talk a bit more, and in 2 minutes, maybe, yeah? So this is a mock-up study that I presented like years ago within models, within CMS. I'm a CMS member. So as a thought of like, the idea was we prepare for positive results. What would we do with a simplified model machinery if we saw positive results? And this was my proposal back then. And since we don't have any positive results, sort of it never got implemented. But the proposal is still, I think, valid. So here, assume you have 2 models that could, so here's the data, okay? Here's one variable, I call it energetic variable. It's the invariant mass of 2 leptons. This is a mock-up, but it is loosely modeled after something we had 5 years ago. There was sort of a mild excess 5 years ago internally, and I set up the whole mock-up study to mimic that's the real analysis. So it's not completely bunkers, but it's also not nowhere near a realistic analysis. So you have 2 features. I call it features in machine learning jargon, or variables. Here's an invariant mass. Here's the angle between the 2 leptons. You have 2 models. Clearly, you see in this model, you expect the angle of the 2 leptons to be very different from this model, because here the leptons are from both branches. And the black dots are the data, so you clear, and these petrol-colored bars are the expected background. Red is sort of the simulated signal. So you see, we assume that there is some mild excess, and now you're asking yourself, should I describe it with this simplified model, or should I describe it with that simplified model, or should I assume that it's a combination of both simplified models? This is much harder than it was in the exclusion case, because in the exclusion case, we said, okay, we don't see anything. If we have that, we give an upper limit. If we have that, we give an upper limit on a cross-section. Here we need to be more careful. Here it's harder, like statistically, because we're dealing with signal hypothesis. So the first step, I'm splitting up the task. This was the proposal. In the first step, I propose a procedure to determine which simplified model or which set of simplified models we use. In a second step, we just infer the parameters of this set of simplified models. The first step is space factors. So the way I set it up is like this. A base factor is basically comes from Bayesian inference. So it's a ratio. It's a ratio of posterior probabilities. And the nice thing is, what you do is basically you integrate out your model parameters, and that has, I mean, we can discuss the statistics in more detail. But what you see here is this is sort of something like a posterior ratio test between model I and SM stands for standard model. And then you can write down the same thing for combination of model I and J over a standard model, and you choose that model that gives you the highest base factor. We can discuss this. The statistics. It's not super hard, but it's not super trivial also. So here, I I did simulations, and I simulated thousands and thousands of LHC runs, and I injected sort of the model Z, a combination of model Z plus W and the model model W. And you see here, I mean, the numbers are fairly meaningless because it's a mock-up study, but you see here when I inject model Z in 70% of the cases, this machinery said you should use model Z to describe the thing. And in 50% of the cases, the machinery said you should use a combination of model Z and model W to describe your signal, and so on and so forth. But yeah, the numbers are meaningless. I just wanted to show that it's not completely bonkers what sort of the base of the machinery gives you. Once you fixed your model, your simplified models, you would infer the parameters. This is fairly easy. You would just do parameter estimating, maximizing. In the simplest case, you just maximize the likelihood. Simplest case here, also the mock-up study, so the specific values are meaningless because it's all fake data. But here you see that already in this fairly simple mock-up study, this is the negative log likelihood as a function of the two parameters, the signal strength and the mass gap between the two parameters of the model. Here is the true value at 100, the delta is 100 GV, strength is normalized to 1. And the only thing I want to point out here is that this already is far away from Gaussian. So it's technically, conceptually it's simple, but technically already one would have to be very careful and understand what a likelihood maximizing procedure is actually doing for real. But in principle, this is what one can do. And then you can estimate an error. You will find that the error is very big. You will find that sort of the estimates of your parameters are very crude. And yeah, and that together, and then you would have the sort of positive results, and you would describe them also in that framework, and then the machines could again play their game. So in summary, my proposal is I do find that this idea of splitting up, factorizing, building up an external model, factorizing the problem into sort of two adversarial machines, this metaphor seems to be, to me, seems very attractive. And it seems to me like model building should also sort of, like everybody is introducing AI these days, why not model building? I think also here we have some space for artificial intelligence to enhance our own intelligence. Yeah, for the theory, the theorists, I mean, something that we could do is models that we're already aware of, we already know, but it would be actually, like, at least conceptually, it would be much more exciting if the AI can come up with any Lagrangian. And then if it finds a Lagrangian, of course, the interpretation of the Lagrangian and the fundamental principles behind that Lagrangian would still be up to the biological intelligence, not to the artificial intelligence. That's just saying. Yeah. In summary, again, I think if we don't exploit the notion of simplified models, I think it'll be very hard, not impossible, but very hard to play the game. So at least in a first inception of that procedure, I would definitely want to invoke simplified models because I think that's realistic in a realistic future. Yeah, we would, of course, like the loss functions, you can play many games, you can find just interesting points, but you could also go for, in the ultimate vision, go for reconstructing really a new standard model. There is lots and lots and lots of technicalities with respect to machine learning and statistics that would have to be addressed. Just to name one is look-elsewhere effect. How would you discuss look-elsewhere effects? Very non-trivial. Of course, interesting would also be, currently we're restrained to SUSY with models. We want to go to results beyond SUSY. We want to discard of our constraint of having to impose Z2 parity. Next question would be, can we sort of like, how can we add data from standard model measurements? And the next question would be, can we even go beyond collider physics? I have no answers here, obviously. Yeah, and as a summary, if you want to join playing a game and finding a Nash equilibrium, I think it could be, I think stuff like that could be a lot of fun, if nothing else. Yeah, thanks.